Welcome.
Instrument based on primitive processing modules.
But it doesn't give a very good idea how much fun it is around here.
Welcome.
Generalized instrument based on primitive processing modules.
But it doesn't give a very good idea how much fun it is around here.
About 16 or 17 years ago when I was in 5th grade, I decided that I needed to make this statement to myself about, must have been 17 or 18 years ago that I was in 5th grade, and I wanted to be very adult about it. At that time there were two things that were, and I really wanted to do what you had to do to be an artist. So being an artist, I concluded after spending a lot of time looking at old art books that my parents used. I'd been thinking about when they were in college. I'd been thinking that I was going to be an artist. To be an artist, one had to draw naked women. Kindergarten doing corny art projects. Now this wasn't something that we ever really did at school. So I didn't have much experience to draw on here. Although at that time I thought engineering was kind of interesting. But I decided I was going to do this anyway. So anyway, I took my pads of paper and I went off to my needed to do something about being an artist. In the woods, where I spent most of my time. One of my pastimes when my parents weren't around was to look at their art books. Some of their art books that they'd used when they were in college, and there was one in particular which I thought it was really neat to draw their some Renaissance, and I remember Renaissance paintings and early American. And I thought I was making these, I don't know, 18th century, 19th century American paintings. And the thing that I concluded after looking at all these paintings was that to be an artist, what you had to do was to draw or paint naked women. So I decided that this is what I was going to do. But I was really convinced to be a great artist, and so I was going to do all this. So anyway, the next thing I decided was that I started drawing naked women. Be old, so I had to save them. I'd get these blank pads of paper, and doing my drawings of naked women, and then I'd make sure they had boobs, Skippy peanut butter jars, and crotch hair, and folded up all my little drawings. I think I tried to make them erotic, although I didn't really know what that was exactly. Peanut butter jars. And I would sit up in my fort, as I said, and playing in the woods was the next most important thing to me. In the woods where so I'd sit in my fort in the woods, and I'd do these drawings. Skippy peanut butter jars. It's all very illicit and everything. I must have buried somewhere after a while. 5 and 10 I started saving them, and I left them there. I collected all these Skippy peanut butter jars. I never went back to get them. Skippy peanut butter jars with pictures of naked women. I wonder if they're still there. It's been then I started digging up the areas in my shelter that I'd built. And I started burying my Skippy peanut butter jars filled with drawings of naked women. They must be so wonderfully funny. I don't know why I started thinking about this again, but that was 17 or 18 years ago. I don't know if they're still there, I wonder. What if somebody found them?
When I was young, I wanted to be a rooster. And then I wanted to be a grown-up.
sleep. Our love is a jungle through which we creep. It's either animal sex or lovers' quarrel. And nothing left to try, 'cause we've done it all.
I want that guitar.
Love you like passion. I love you like passion.
At times, I could deflect the bullets from a magnum aimed at your heart. At times, I could be with the lines disappearing between pleasure and pain, with love and hate becoming one and the same. As I suffer the orgasm and enjoy all the pain, it's all the same, or is it you?
At what's called the world's most popular science museum in Chicago, they're getting to both see and touch the art of science, computer graphics.
They're seeing images that they've never seen before. These images do not exist in nature. They come out of mathematical processes. The only way to see them is with a computer. So it's a new world.
Artist-scientists at the Electronic Visualization Lab at the University of Illinois at Chicago have put together the interactive image. It's an exhibit that allows museum goers to create their own computer images.
I love it. It's neat. It's art, and you can do so many things with it.
It brings poetic images to my head. It brings words, it brings metaphors.
Through the use of computer hardware and software programs that seem more like games, you can create your own laser light show, examine massive sets of numbers visible only as complex geometric patterns, and learn the fundamentals of computer animation. The developers hope to give museum visitors a chance for mental exercise they don't ordinarily get.
Half of our neurons, half of our brain is devoted to visual processing. And when we use computers without visuals, we're throwing away half of our brain.
We use the word see to mean understand, and it's because we understand so much about our world visually.
The exhibit is designed to challenge anyone from a 3-year-old to a research mathematician. In a game called Complex Images from Simple Rules, players create their own plant or tree-like objects by giving the computer a set of instructions.
Oh, cool, look at this.
In another, your own image is digitally processed to reveal just how much information is in an image. The exhibit also reveals that humans don't need to see detailed images to recognize what they are. In yet another, complex sets of numbers are portrayed on a computer screen, and players manipulate them with visually exciting results.
This is math. I'm in geometry now, and math is not like this.
For years, computers have been used as a learning tool, but generally that's meant a lot of words on the screen. Not so here. The interactive image is providing a whole new way of looking at computers. I'm Jeff Flock, CNN, at the Museum of Science and Industry in Chicago.
There is more information here than you can see in this static pattern. When I slowly step between frames, you can see that there is a general organization of the random dot pattern. But only when I animate do you see that there is a square moving to the left. This is a simple-minded illustration of why animation is necessary for certain kinds of scientific visualization. There is phenomena in the world that you only see when it's moving. When this square stops, you will no longer be able to see the information.
AZT, the azidothiamidine molecule, is shown here in a stick figure representation. Here it is superimposed on thymidine, a part of DNA produced after HIV infection. AZT is used in the treatment of persons with AIDS. Its effect is presumably due to its similarity to thymidine. This model emphasizes the bonds between the atoms in AZT. In another model, the atoms are shown as spheres. However, it is really the electrons that are doing the chemistry, and in order to study this effect, we performed Gaussian 86 calculations on AZT and rendered the electron density in the highest occupied molecular orbital. Here, the growing electron density represents lower and lower electron densities around the nuclei. The higher electron density contours become visible when we render the lower densities transparently. Here, thymadine's electron density is shown using the same colors and contour levels. In this volume visualization, we used a volume of 200 by 160 by 140 voxels and rendered the contours using small spheres. In order to understand the effect of AZT, we need to look carefully at not just the similarities, but the differences between AZT and thymidine. To do this, we have carefully aligned AZT with thymidine and subtracted corresponding elements of the two voxel matrices representing the electron density of AZT and thymidine. Contouring in the same way as before, we clearly see the lower electron densities of AZT shown in purple and blue, and the greater electron densities in shades of green. Using this difference technique, we can suggest new molecules. Computational chemistry provides not the answers, but a rational basis for drug design.
This is a model of a papillomavirus which has been ray traced. Ray tracing provides a high degree of realism because it simulates the way light bounces off an object into the viewer's eyes. This model is made up of 3D geometric shapes such as spheres and dodecahedrons. It takes us about 6 minutes per frame to make this image. Our computations are done on an AT&T pixel machine. They would take about 500 times longer on a 386 PC. Ray tracing simulates light by bouncing rays of light around the scene like they were billiard balls. This allows for a good representation of important optical details such as shadows, reflections, and refractions. Basically, it lets you see better. This type of fractal is called a quaternion Julia set. It is produced by a simple equation, z equals z squared plus k, which feeds its output back into its input many times. The result shown here is the map of the behavior of an equation which cannot be represented by a simple combination of geometric objects, such as in the papillomavirus shown earlier. We have developed new ray tracing techniques to see fractal objects better. As we zoom in on geometric primitives like planes, spheres, and dodecahedrons, the view becomes simpler and simpler, since geometry of this type can specify detail at only one level. As we zoom in on fractal objects, the view does not simplify, since fractal geometry specifies infinite detail. This is a feature of fractals that is of high interest because many natural phenomena, such as weather, also have meaningful detail on all scales. The basic geometry behind ray tracing has been understood by artists for a long time. Of course, what's important about this image is not the reclining nude, but the grid. In The Designer of the Lying Woman by Dürer, the draftsman is sighting a ray through the grid to the lying woman. This is exactly what is happening in ray tracing. The ray tracer simulates the behavior of light by casting a ray from the eye through the grid out into the space to be ray traced. It has to cast a ray through every element of the grid. On the computer, these elements are called pixels. There are a lot of pixels used to represent an image, at least 250,000, and in many cases, millions of pixels. For each pixel, quite a bit of computation has to be done. This is why ray tracing takes so long. The first piece of computation is to calculate the intersection of the ray with the object to be ray traced. After that, a tangent plane is calculated so that the ray can be bounced properly with an angle equal to the angle which the ray comes into the object. Fractals are monstrous to ray trace. There is no known equation for the intersection of a line and a fractal. And also, fractals are infinitely rough, so there is no flat area to calculate a tangent plane to properly bounce the ray. At EVL, we have been developing new techniques to ray trace these monstrous objects. One could ray trace a fractal object by making very small steps along the ray and iterating z equals z squared plus k hundreds or thousands of times at each step. Small steps are necessary to not miss small details. This is a very slow process. We probably don't want to wait for the results. Eventually, it'll get to the fractal object. For some fractals, we can estimate the distance from any point along the ray to the fractal object. The distance estimate is indicated by blue spheres. At any step, we know the fractal to be outside, not inside the blue spheres. Therefore, we can step along the ray by the radius of the sphere, calculate a new distance estimate, and step by that radius. Although this is not as fast as calculating the intersection of a ray with simple objects, It is much faster than stepping along the ray by tiny steps. After we find the point of intersection, we need to calculate the angle between the incoming ray and the fractal object. We do this by surrounding the point of intersection with a three-dimensional grid. At each cell of the three-dimensional grid, we calculate the distance to the fractal object. Here, lightness indicates distance. Cells opposite the center of the grid are subtracted. Those differences are added together to find out an angle which is away from the fractal object. Perpendicular to that line, we construct the tangent plane and bounce the ray. We use these techniques to visualize at high quality mathematical objects that have never been seen before.